Hello everyone, welcome back. This is lesson 7.2.3. And today we are doing more proofs. We are looking at what else can be proved. So this first proof, we're looking at the relationship between rectangles and parallelograms. And we are supposed to prove that all rectangles are parallelograms. And the way we can prove this is by taking a generic rectangle that I've drawn over here and basically proving that it is a parallelogram. And because it was generic, this basically implies that that's the case for all rectangles. So it's giving us a little hint here. It's telling us to prove that opposite sides must be parallel. So that's kind of what our end goal is. So let's start with a rectangle. We've talked about a couple of things with rectangles. We know that opposite sides are congruent, so we can go ahead and mark that up. We know that with diagonals, those have a shared side. Diagonals are congruent. And basically, with this kind of proof, if I'm looking at, I want to prove something about one part of this shape, that kind of gives me a hint of maybe wanting to use CPC-TC. And the way I've described this to my students is if we're talking about my face and the left side of my face is equal to the right side of my face, I'm allowed to say that my left eyeball is equal to my right eyeball. So if I can maybe prove, let's maybe just look at one of these diagonals. If I can maybe prove that one triangle is equal to the other triangle, I could then start saying things about their individual parts. And that's maybe where I want to go with this proof. So I'm going to go ahead and label my rectangle here. I'm going to go A, B, C, D. So I'm going to start maybe with the information that I'm given, see if that takes me anywhere. I'm going to talk about how opposite sides are congruent. So side AB is congruent to side DC. And my reasoning for this, well, that's just due to the definition of a rectangle. I know that about rectangles, so I can use that. I'm going to say the same about the other opposite side pair. So AD is congruent to BC. And again, I'm using lines over those to show that they are line segments. And that again is a definition of a rectangle. Now, in order to use CPC-TC, I need to prove that triangles are congruent. And when I'm trying to prove congruency of triangles, I am looking for one of these congruence postulates. So I've kind of already shown that we have two sets of congruent sides here. And so when I'm looking at my postulates, I'm going to look at the ones that have two sets of congruent sides. So those might be good ones to use to prove that these two triangles are congruent inside the rectangle. And so maybe I'm looking for another angle or another side that I could prove is congruent. One thing that stands out to me, this is one of my favorites, is when there's a shared side that we have been starting to call the reflexive property, and I have that as side AC here. So I think I'm going to use side, side, side to prove that these triangles are congruent. So I'm going to add that in here as another bubble. AC is congruent to AC, and this is because of the reflexive property. And these three pieces of information, side, side, and side, tell me that my rectangle, or I'm sorry, that the two triangles are congruent. So the first triangle I can call triangle ADC. And this is congruent to triangle CBA. And this is because of side, side, side congruency. Again, this part is not really new to us so much as the explanations are, okay? Writing in those justifications is newer to us, and we kind of had to piece some of this information together. Okay, so I've proved that these two triangles are congruent. However, my end goal is to prove that the opposite sides must be parallel. And when I see this, my word association here with opposite sides being parallel should be that alternate interior angles are congruent. Okay, those are the two that really go together. If we look at our proof help, okay, if we're talking about opposite sides are parallel, we should be thinking about how alternate interior angles are congruent. That's kind of where our mind should be leading us. So let's see if I can prove that alternate interior angles are congruent. Because my two triangles are congruent, I'm allowed to pick on little parts of the triangles. For instance, corresponding angles. So angle BAC here and angle DCA, those are equal, kind of like saying my left eyeball is equal to my right eyeball because I've proven that the left side of my face is equal to the right side of my face. And those are alternate interior angles. So I'm on the right track here. So I'm going to say angle BAC is congruent to angle ACD. And the reason I can say this, again, is because of CPCTC. Corresponding parts of congruent triangles are congruent. And I could say this about the other set of alternate interior angles. So angle, this is now DAC, with the two loops, is congruent to angle BCA. And again, that is due to CPCTC. And at this time, I have proven that these alternate interior angles, both sets of them, are congruent, which means those opposite sides that go with them are parallel. So from here, I can say that, and I'm running out of room, so sorry. But here I can say that AB is parallel to DC. And that's the symbol for parallel. And because of this set of alternate interior angles, I can say that AD is parallel to BC. And that is because alternate interior angles. And I guess that's really the converse. That says if alternate interior angles are congruent, then our lines are parallel. All right, I have proven that opposite sides must be parallel. And it took me a lot to get here. And there's actually a couple different ways you could have done this proof. This is just one of them, okay? And so when it comes to taking an assessment, what we're really looking for is, can you come up with reasonings for things, and can you kind of find a natural flow to get from the start to the end? So if you had done this proof on your own and then watched this video, there's a chance that your proof looked a lot different than mine, but still was a good proof. So just keep that in mind, that if your brain didn't naturally flow in this direction, that is okay. So this was a good example of using CPCTC in a proof to basically show that two little parts are the same, because we proved that two triangles are the same, are congruent. All right, let's take a break from official proofs for a second and come down here. We are wanting to solve for x. Okay, and we're also trying to state which triangle congruent statement was used. And reminder, those options are side, 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 angle, side, angle, side, angle, 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 side, or hypotenuse leg. So hopefully Pythagorean theorem isn't something that you've forgotten about. I've got a triangle with two known sides here, and it's a right triangle, so I can find the third side using Pythagorean theorem. Let's call this missing side y for right now. So because our hypotenuse has to be c in a squared plus b squared equals c squared, I'm going to plug in the 10 for c. This would get me 64 plus y squared equals 100. So y squared equals 36, and y is 6 when I take the square root of both sides. So I'm going to replace that y with a 6. Now, with these two triangles here, these are both right angles. Whoops. These are both right angles here. I have two congruent sides, and I have a shared side due to reflexive property. So these triangles are congruent due to angle, side, angle. And so because I just found out that this side was 6, I can also say that x is 6 as well. So x equals 6. And I found this due to using Pythagorean theorem. And again, that's a squared plus b squared equals c squared. And I also used ASA congruency to find x. Moving on to the next one here. Here I am given two congruent angles. I have a shared side due to the reflexive property here. And these arrows tell me these are parallel lines. And when you think parallel lines, you better be thinking about alternate interior angles. So I'm going to label that I have a set of alternate interior angles here that are congruent. And I now have two triangles with angle, side, angle, congruency. Angle, side, angle, congruency. So these triangles are congruent, which means that their corresponding parts are also congruent. So I'm going to write down that I used angle, side, angle. These triangles are congruent. So we have two corresponding parts here. This side x here corresponds with the side that is 10. And because of CPCTC, those sides are congruent because both triangles are congruent. So x is simply 10. And I used ASA and CPCTC for that. On this next one, we are bringing back trigonometry to solve this one. Okay, we have an angle here that we know, a side, and we are looking for a missing side. So the first step is to label our sides. Maybe I will call this one y for right now. This is opposite, adjacent, and hypotenuse. So if I am looking to find this y right here, because I am looking to find x, the opposite side, I'm going to want to use tangent, because that is opposite over adjacent. Tangent of 35 equals 11 over y. When you end up cross multiplying these, you get y times tangent of 35 equals 11. So then to get y by itself, you would divide by tangent of 35. Again, this is from last unit. And for y, when we do that, we end up getting 15.7. So we found that side. I'm going to do a little bit of erasing real quick. This side is 15.7. We do have congruent angles, but this one is actually going to be a hypotenuse leg congruency problem because we have a shared side here that happens to be a hypotenuse because it's across from the right angle. And we were also given two matching legs. So because of hypotenuse leg, these triangles are congruent. So if this side is 15.7, then X is 15.7 due to CPCTC. So X is 15.7. Finally, with this problem, AC and BD are straight line segments. With this one, I'm just going to say right now that we do not have enough information to solve for that one. And we're going to move on to this proof. Now this should look familiar. We did already solve it. We solved for X. But right now I want to prove that AD is congruent to BC. So I'm going to cross out that X. We're not trying to solve for that. We are trying to prove that AD is congruent to BC. We did that algebraically, but now we're going to write a proof for it. So one thing that I'm going to start with is with the things that I am given. So I have some arrows here on AB and DC, which means that they're parallel. So I'm going to go ahead and write that information down. Side AB is parallel with side CD. And that was given to me. And that means that alternate interior angles are congruent. I actually already have a pair of angles that are congruent, so I'm going to go ahead and write those down as well as given. So that is angle ADB is congruent to angle DBC. That was given to me. Those are those angles I just labeled in green. I will talk about how these parallel lines mean that that other pair of angles are congruent because they're alternate interior angles, so I'll go ahead and talk about those right here. So angle ABD is congruent to angle CDB. And that is because they are alternate interior angles. So I've got one set of angles that are congruent in the pink, another set of angles that are congruent in the green, and I have a shared side there due to the reflexive property. So I'm going to say DB is congruent to DB because of the reflexive property. And lo and behold, I have a case of angle-side angle congruency. I have those two angles and a side between them. So that is enough to say that these triangles are congruent. So triangle ABD is congruent to triangle CDB. That is due to angle-side angle congruency. This is where I get to use CPCTC. I've proven that both triangles are congruent to each other, so I can pick on little parts of the triangles and say those are congruent. I was trying to prove that AD was congruent to BC. That's like saying left eyeball is equal to right eyeball because I've proven left face is equal to right face. So because of this, I can say that AD is congruent to BC, and that is because of our probably new favorite at this point, CPCTC. And we're done with that proof.